Kevin, could you shut the door while you're up, please? Could you shut the door while you're up? Thanks. All right, so if you recall, last day we had a strong base, we had the hydroxide ion, and it was reacting with a weak acid, and we reacted half of the weak acids. And now we need to open the door, because apparently it's locked. Thank you. Okay. So we had reacted half of it, which means that we have half of it still as the CH3COOH, right? So we have 2 millimoles of that. And then half of it has been turned into CH3COO minus, the conjugate base. So what you have is you have the concentration, or sorry, the moles of HA are equal to the moles of A minus, yes? And it's all in one container, so we can find the concentration. Yes, so we have now the concentration of HA is the same as the concentration of A minus. So that's when we've exactly reacted half of it. Those two are the same. And we can throw that all into a rice table, which we did here, blah, blah, blah. And we assumed X was insignificant. And when we assume X is insignificant, if the base form and the acid form are equal, then what do those do? They cancel out, right? Whoopsie. And so all we're left with is that X is equal to the Ka, and X, if we're like, what is X again? X is the concentration of the hydrogen ion, okay? So what we end up with is Ka is equal to the concentration of H plus. So at the half equivalence point, the concentration of H plus, so we label it like this with a little 1/2 at the bottom, okay? H plus at the half equivalence point is equal to the Ka. And we can take the negative log of both sides. That finds the p-value, yes? So the pH at the half equivalence point is equal to the pKa, yeah? All right, so that's where we got to last time. I don't know that it is really worth our while to do the same calculation with the base. You can do exactly the same calculation, but you would start with the weak base equilibrium. Maybe what you could do is you could just write the weak base equilibrium here. Why don't we do that? Okay. So write the weak base equilibrium that involves CH3COOH and CH3COO minus. Did you guys get what I got? Yeah, okay. Now, you could put in your rice table, you would still have 0.333 molar, 0.333 molar. You would have 0 for the hydroxide. So which way would it shift? It would shift to the right. and you would end up with 0.333 minus x, 0.333 plus x, and OH is x. And what would you do with each of these x's? Yeah, you would assume insignificant. Okay. And then you would go through and you would do the whole KB calculation. Is it worthwhile doing that or no? Yes, it's worthwhile doing it? Okay. So this has hydroxide here. Okay. And if it has hydroxide, what kind of K value do we want to use? We want to use KB. Okay, so KB is equal to KW over what? Ka of the conjugate acid, and the conjugate acid of CH3COO minus is CH3COOH. So that's 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. And we get 5.6 times 10 to the negative 10, I think. 9, 10? Let me check. 1, E14 negative, divided by 1.8, E5 negative equals 5.6 times 10 to the negative 10. Okay. So we have that value, and then we would go through and we would say, okay, I write my KB expression. KB is equal to CH3COOH times OH minus over CH3COO minus, and KB is 5.6. That doesn't look like a 5 point anything. There we go. 5.6 times 10 to the negative 10 is equal to 0.333 times x divided by 0.333. And look, once again, we're at that point where they are exactly equal to each other. And remember, the x represents the concentration of OH minus. And remember that this is the KB. And what do we call that point that we're at where we have reacted half of the acid? We are at the half equivalence point. So we can say OH 1/2 at the half equivalence point is equal to KB. And if we do all the math, we will actually end up with the same value as we did back here. Okay? We should end up with pH of 4.74. So let's see if we do. So concentration of OH minus at the half equivalence point is 5.6 times 10 to the negative 10. And the POH is negative log 5.6 times 10 to the negative 10 equals 9.255, and so pH then is 14.00 minus 9.255, 4.74. What did we get when we used the acid equilibrium, we got pH equals 4.74. So it doesn't matter whether you use the Ka, the acid equilibrium, or whether you use the base equilibrium, you'll get the same result. Okay? Yes? We good? And I think I just have, I'm not sure why I have 2 copies of this. Anyway, just ignore me. I don't know why I've got 2 of those. Now we're going to skip on to page 69. All right. When all of the weak acid is neutralized. Ooh, this is exciting. So we have the same moles or we have the same volume and molarity, 5 milliliters, 1 molar NaOH, and we have 5 milliliters, 1 mole of the acid. Okay, so those are the same. Please tell your partner, if you can, how many millimoles of NaOH this is. Remember, you have 5 milliliters times 1 mole per liter, which gives you 5 millimoles. Yes? So we have 5 millimoles here, and we have 5 millimoles here. What is our total volume, just for later? Our total volume for later is 5 plus 5 is 10 milliliters total volume. So we're going to do a RICFA table. Why do we use the F here instead of an E? Chat with your neighbor about that. Why are we using an F instead of an E? Yeah, we have a one-way arrow, so it goes to completion. So we don't have an equilibrium concentration. We have a final concentration. Okay, so neither reactant is in excess, yes? What do we call this point? If we were doing a titration, what would this point be called? Where neither is in excess. We've just reacted them perfectly. It is the equivalence point. Okay, the equivalence point is where nothing is left over. You don't have any excess acid, you don't have any excess base. You have just reacted it perfectly with each other according to the stoichiometry. It is also called the stoichiometric point, because if you look at the ratio, you have 5 millimoles to 5 millimoles, which is 1 to 1, and the ratio from the equation is 1 to 1. So the numbers of the substances match the coefficients. Does that make sense? Stoichiometric point. Okay, anywho, that's our equivalence point. So all of the acid has had its hydrogen ripped off, and so all of the acid has turned into its conjugate base. All right, so we started with none of it, and none of the conjugate base, and then it made 5 millimoles, so we now have 5 millimoles of the conjugate base. So I don't have any OH, I don't have any CH3COOH. All I have left is CH3COO minus. And what kind of species is CH3COO minus? It is a base. So would you expect this solution to be acidic, basic, or neutral? Basic, yeah? So this is the base. And therefore, the solution will be basic at the equivalence point. Now, if I was just to ask you, if you have the same number of moles of acid and base and you put them together, what's the pH? What would you say? If you have the same moles of acid and base and you put them together, what's the pH? 7, except it's not, it's basic. You just told me that. Yeah? So it's not 7. Oh, because 7 is neutral. So if you are reacting a strong base with a weak acid, you are going to produce a basic salt. Okay, the reason you think it's pH 7 is because up until now we've been reacting a strong base and a strong acid, and the salt we get is a neutral salt. There is no hydrolysis. But the moment you put a strong acid with a weak base or a weak acid with a strong base, you get a salt which is either going to be an acidic salt or a basic salt. Okay? So we'll come back to that again later because it is a bit of a transformation in your brain, because I know if I was to say to you tomorrow, you know, what was the pH when you react exact moles of an acid and a base, you would have to say, I don't know, but probably most of you would still say 7. Right? Because that's so ingrained in your brain. It's like when it's completely neutralized, I have completely neutralized the acid. What's the pH? Oh, it's 7. No, it's not. Okay, so we're gonna keep repeating over and over again that we get these acidic salts or we get these basic salts. Okay, so what we've got then is we have our 0.5 molar CH3COO minus, and that is the only thing that we have. And so we can do a weak base equilibrium because this is a base. All right, we put it with water, we get CH3COOH, and we get OH minus, and we go bam, 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 plus X minus X, et cetera, et cetera. You need to find the KB value. Okay, so this is a separate calculation, which is going to let you take this number and pop it in over here. Yes? So, solve for X, find the PA, this is P, the X is OH, find the POH, and that gives us our, what is happening here? I feel like this is like leftover from something else. Just cross that out. Fix. I think I copied and pasted from somewhere else, and I did not get rid of that. Okay, so we have a pH of 9.22. Which is, as we said before, going to be, that is a basic pH. And now we have one more situation. We started with having excess acid. We had not reacted all the acid. Then we reacted half the acid. And then we reacted all of the acid, but just perfectly. And now we're going to keep adding a little more base so that we have excess of the strong base. So we're going to have excess strong base. So we have 6 milliliters of 1 molar NaOH. How many millimoles of NaOH do we have? 6 millimoles, okay? And that's going to go into our RICFA table. We have 4 milliliters of 1 molar of the acid. So you can see we have more of the base than we do of the acid. So this is 4 millimoles. That goes in here. Who is the excess reactant and who is the limiting reactant? Tell your partner. Who is the excess reactant and who is the limiting reactant? Remember, the limiting reactant is all used up, yes? And the excess reactant, there is some left over. So who is the limiting reactant? This one. I'm just going to call it the LR, okay? That's our limiting reactant, and it gets all used up, all gone. And that means that our OH minus is the excess reactant, and so there is some left over. And because it was -4 and -4, this goes up by +4. Okay, and so we end up with 4 millimoles of CH3COO minus. That's the weak base, okay? So we have 2 things right now. We have OH minus and we have CH3COO minus, all right? So we can figure out our concentrations because, again, 6 milliliters and 4 milliliters gives us 10 milliliters. So 2 millimoles in 10 milliliters gives us 0.2 molar OH minus. 4 millimoles, whoa, that wasn't what was supposed to happen. 4 millimoles in 10 milliliters, that gives us 0.4 molar CH3COO minus. And because we've worked with milli, the millis cancel there. You could do it all in liters though, and that's totally fine if you feel better that way. Now, this is a weak base. How much do weak bases produce of OH? Not a whole lot. So our weak base, the CH3COO minus, it will produce OH. Okay, so the weak base, CH3COO minus, it will produce OH, but the amount it produces is insignificant next to the hydroxide left over from the NaOH. And if you're like, I don't know, could you prove it to me? I could say, yes, I could prove it to you. We could do a race table. We could be like, I got 0.4 molar of my weak base. And I got 0, and I got 0. Oh, I don't have 0 of the hydroxide. I have 0.2 molar hydroxide, right? Yeah, okay. Now, if I do this, blah, 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 so I end up with, here's my KB calculation. That's sort of separate. I plug that value in here. I assume that X is insignificant to make my calculation easier. When I solve for X, I end up with 1.1 times 10 to the minus 9. Is that insignificant compared with 0.200 molar? Yes, it is. Okay, so it was a correct assumption to make that it was small. Okay, so after the equivalence point, this is once we've gone past the point where moles of acid and moles of base are equal, the OH, the POH, the pH, and the H depend only on the amount of strong base in excess. Okay, so you're only worried about that OH concentration. Okay. Okay, so here's a summary. Before the equivalence point, you have some weak acid, HA, and some weak acid has turned into its conjugate base. So you have some conjugate base, A minus. So you have both HA and A minus. You're not going to have to do these calculations, okay? You're not responsible for these calculations. But if you're at university and you're doing a titration and you're like, oh, I remember there was a calculation section on finding the pH before the equivalence point, you could refer back to this. Anyway, use a Ricfa table, use a Rice table, whatever, okay? At the half equivalence point, that is when half of the weak acid remains and half has been converted into the conjugate base. And what that means is that HA is equal to A minus, and you can just use H plus at the half equivalence point is equal to Ka, and you do need to know this. At the equivalence point, all of the weak acid has been turned into its conjugate base. So all we have is the conjugate base. So only the conjugate base is present. And again, you don't need to do, oh yeah, you might have to do these calculations. So you would find the moles of A using a Ricfa table, okay? And then you would divide A by the total volume, and then you would do a weak base equilibrium with Rice and Kb to find OH. A question like this would be challenging. It would be like a, you know, one of those ones that says like at the end of the test, right? You'd be like, oh, damn, right? And what happens after the equivalence point? After the equivalence point, there is excess OH. We do have some conjugate base, but the conjugate base is, the weak base is insignificant compared with the OH. And then there's a summary of the summary. If you've added no base, you have only HA, use Rice and Ka. If you are before the equivalence point, you have both HA and A minus, use Rice and Ka. At the half equivalence point, you have moles of HA equal moles of A minus, or you could say that concentration of HA is equal to the concentration of A minus, and you can use, I mean, you could do Rice and Ka, it just takes a lot longer. Okay, and you would use the pH 1/2 equals pKa or H plus 1/2 equals Ka. At the equivalence point, you have only A minus because you've turned all the acid into base. You would use Rice and Kb. After the equivalence point, you have excess OH and you have A minus also present, but it is insignificant. And so you just take your moles of OH over the total volume, and that's it. So we've actually sort of looked at titration curves here, but we haven't looked at the actual diagrams themselves. So we'll get to that very soon. Okay, so that's it for that. There are some exercises here. I'm going to just circle the ones that you should do, okay, because you don't need to do all of them. That one, that one, that one, 1, 2, and 3. Five and 6. And 7. So when I said not all of them, I meant don't do number 4. If you want to do number 4, if you're like, just for completion, I should do number 4, you can do number 4, okay? All right. So are we good with that? All right. Can we move on to buffers? Yes, because otherwise we'll never finish this unit and we'll never get to electrochemistry. There are a bunch of videos here that I am not going to show you, but should you want to watch me teaching buffers, I teach buffers here and I teach buffers here. And if you're like, Miss Spence, those videos total 55 minutes. You could watch Mr. Colger for 13 minutes, 7 minutes, 5 minutes and 14 seconds. That's a lot less, right? You're like, oh, that sounds pretty good. Okay. However, we're going to go over buffers today, so you might not need to watch it at all. All right, so we're now on page 76. I would like to have a quiz on hydrolysis and mixtures of strong acids and strong bases next Monday. Is good? Huh? My marker is so bad. Yeah, I know. Why don't we just throw that one out so I'm not tempted to use it anymore? Okay? Because it's not useful. Is good though? Okay. Did you guys do okay on the hydrolysis questions that I gave you yesterday? Those were all right? You know how to compare the Ka and the Kb to figure out if it's acidic or basic? I'm seeing all the people nodding who I know regularly get A's on all their tests. So how about the people who don't always necessarily get an A on their test? How do you feel about comparing Ka and Kb in hydrolysis to figure out whether it's acidic or basic? Nobody's willing to say anything. Okay, come see me Monday morning or after school today if you have any questions about it. All right. Buffer solutions. A buffer solution, you may have come across it in biology if you've taken biology 12. It is a solution which resists a change in pH. Okay? And it resists a change in pH when we add a small amount, not a huge amount, but a small amount of strong acid or strong base. So what it's doing is it is minimizing the change in pH when you add acid or base. And we can analyze a buffer solution using a Rice table. Okay? So let's say that we have some 1 molar acetic acid CH3COOH, and we get our equilibrium. okay? And you do all the calculations and it ends up being 0.004, 0.004, and 1. Okay, we're not going to do the actual math. You're just going to have to believe me, okay? Now, because it is weak, these concentrations here are quite low at equilibrium. Yes? Okay. So here's a question for you. Will the shifting of this equilibrium be effective at bringing H3O plus back to close to its original if we add 0.1 molar NaOH? Will it be able to shift to get H3O plus back to close to what it originally was? Chat with your partner about that. And if you're not chatting, you should start chatting. What are we really adding if we're adding NaOH? Which ion are we interested in? We're interested in the OH minus. What can the OH minus do to this equilibrium up here? It can react with the H3O plus, which will decrease concentration of H3O plus. Okay, and if the concentration of H3O plus is decreased, what can the system do? It can shift to the right. What will that do to the concentration of H3O plus? It will cause it to increase. Now, let's just do a quick little diagram here. We have lots, this is our concentration, yes. We have lots of, I'm just going to call this HA because I don't have room to write it out. Okay, so this is lots of HA. And we have H3O plus, which is quite small, yes. H3O plus is small here. And when we add NaOH, what happens to the concentration of H3O plus? It spikes downward, yeah? And then the system shifts to the right. As it shifts to the right, what happens to the concentration of H3O plus? It goes back up. Does it get to quite its original value? No, but it's pretty close, right? Okay. And what happens to the concentration of HA? It decreases by the same amount because it's 1:1, okay? There we go. All right. So we could do that a few times in a row, yes? If we wanted to, we could keep doing that for a while. All right, because we've got lots of the HA around. What would happen then if we added 0.1 molar HCl? This would cause, HCl would cause what change to this equilibrium? Increase in concentration of hydronium, and that's going to cause a shift to the left. Now let's see what that looks like, okay? This is 0.004. Yes. And this is actually both the H3O plus and the CH3CO. This is A minus. So this is both A minus and H3O plus. They're both very low, right? Those concentrations are very low. And our concentration of our HA is quite high. I can't even draw it to scale, right? Like this would actually be like 10,000 times smaller on the graph, but I can't draw that well. So, whoa. Now I add some H3O plus. So it increases quite a bit. Actually, it's 0.1 molar, so it would be like this much. Now, as it shifts to the left, what species get used up? Both H3O plus and A minus. Here goes our A minus. Thunk. Can you go below 0? No. So how far can this shift back? Thunk. We have run out of the other reactant that the H needs to react with to actually make it shift. Yes? So we are limited in how much it can actually shift. And if I added more, this would just keep going up. If I added more, sorry, what am I doing? Pen, where are you? There you go. Oh, no, I don't want that. There we go. If I added more, it can't shift. There's nothing left for it to react with. We will use up all of this in the first little reaction. So is it able to buffer? No. It's able to buffer NaOH, but it is not able to buffer HCl. Because we just run out of stuff. Like H, in order to go this way, you need 2 reactants. You need CH3COO and you need H+. If you run out of CH3COO, H3O plus has nothing to react with and that equilibrium cannot shift. So is this situation here just plain old acetic acid? Is that a good buffer? It's not a good buffer because it can resist a change if we add some strong base, but not if we add strong acid. And a buffer solution can do both. All right? What would we need to have more of in order for this to be able to shift to the left? We would need to have a lot more of this thing, right? In order to be able to shift to the left. Can you think of a way we could add more CH3COO minus without just adding more of the acid? You might think back to your solubility unit when you wanted to add an ion. NaCH3COO minus. So you can add that base all on its own, but just it has to be partnered up with a cation, and you would choose a non-reactive cation like sodium, okay? So what we're going to do now is we are going to add some sodium acetate to the equilibrium mixture so that now acetate is also 1 molar. So when we do this, the acetate concentration goes which way? It goes up. In response to this, the equilibrium will shift to the left. And if it shifts to the left, what has happened to the hydrogen ion concentration? It has decreased. So the hydrogen ion concentration has decreased, and the acetic acid has increased. So what we have now is we now have acetic acid, which is a little bit bigger than 1 molar because we shifted towards the acetic acid. The concentration of acetate is a little less than a molar because 1 molar because we shifted away from it. And the concentration of the H plus or the H3O plus is very, very low. Okay? The moral of this story is we now have both a high concentration of the weak acid and a high concentration of the weak base. So when we look at this equilibrium here, will it be effective at bringing H3O back to close to its original concentration if we add NaOH? If we add NaOH, H3O plus decreases, yes? And this would shift to the right, and we have lots of this so it can do that, okay? So yes. Now, what if we add some H3O plus, some HCl? That's going to bring the H3O plus up, which will cause it to shift to the left. Do we have enough of this stuff to shift to the left now? Yeah, because we have lots of this. So now we're able to resist a change in pH in both directions. So this solution is an effective buffer. Now, sometimes I get people saying, oh, I just mixed an acid and a base together. Don't they just neutralize each other? No, that only happens if you put a strong acid or a strong base in there. When you have the two weak ones, you just end up with an equilibrium, which is one of the reasons why we don't have you calculate pHs when you start mixing different weak acids and weak bases. It's just too crazy. Okay? So whenever you mix a weak acid and a weak base, they just hang out in equilibrium with each other. And it is the shifting that allows the buffer to either use up most of the extra OH when we add a strong acid, or to produce more H3O plus to replace the stuff that reacts when we add a strong base. So what you're going to do now is you're going to describe the stress, the shift, and the overall change in H3O plus and the overall change in pH when each of these are added to the system. So we're looking at HCl for A and NaOH for B. So try filling that out. So folks, when you're doing the stress, be sure that you reference chemicals that are in the equilibrium. The stress for NaOH is not an increase in the concentration of OH, right? Because OH is not part of that equilibrium. The stress is a decrease in H3O plus because that ion is part of the equilibrium, okay? Oh, in more detail. Oh, good Lord. Do we really want to do this? I think we kind of did this. Yeah, we kind of did this already. Okay, so we've got, if we add some HCl, our hydrogen ion concentration goes up, and then it shifts to the left, and the hydrogen ion concentration comes back down again, but there's a very small net increase. So the pH will decrease, but only by a small amount. Could you... Oh, didn't we just do that? This should be when a small amount of... Should we do NaOH? Because this is stupid if it's just HCl again. Let's do it when NaOH is added to the buffer. Oh no, it is pH versus time. We do want a... Oh my God, what is wrong with me? Oh, so sorry. So the H plus went up, so the pH will go down. And then it will come back up to close to its original value, but not quite there. Yeah? Same buffer solution, we're adding OH. We've already talked this through, but you can see when we added our NaOH, the H3O plus dropped. But the pH, but it shifted and we got more of the H3O plus being made as the equilibrium shifts to the right. Could you draw the pH versus time when we add NaOH? Is good? Okay. We already talked about this. This is just sort of going over when if we didn't have enough of the base, you cannot actually shift to the left. So I'm not going to read through all of that, but I'm just going to highlight the key point here that the buffer must have relatively large concentrations. And by relatively large, that usually means 0.2 molar or more. And then I'm going to put ish, because really you can have less than that if you're planning on adding less acid, right? You can buffer a small amount of acid the lower the concentrations are. The higher the concentrations are, the more addition of acid you can buffer and the more addition of base you can buffer. But usually if it were me and I was like, somebody said, make me a buffer system, I would just say 1 molar because that's a pretty high concentration. It's a nice round, even number. Yes? 1 molar is a good number. You know what I mean? Right? You could also choose 0.5 molar because it's also fairly large and just a nice round number. Okay? So it has to have really relatively large concentrations of both the weak acid and the conjugate base. And remember, this is just going over, can you go get CH3COO minus ions on their own? No. Who's a good ion to pair it up with? Something like Na or K that will not hydrolyze. Okay, so you cannot just add the weak acid. You need to have the weak acid and the salt of the conjugate base. So if you have a weak acid and the salt of a conjugate base, that is a buffer. And I think that's a good place to stop for today. Okay? So your homework is page 74, omit number 4. Huh? Or do you just want to study for your quiz? Study for your quiz. Because it is on Monday. And that is on strong acid, strong base combinations. So that is section 5.3. 5.3 and 5.4, but not 5.4c. Okay? 5.3 and 5.4a and b. 5.4c is more sort of to get us into the realm of buffers and titrations. It's sort of like the preview to that. So 5.3, strong acid, strong base. 5.4, A and B. So your test on this unit will not be next week because I like you to have a weekend to study, right? So it'll be the week after, but we might finish up and start. Well, actually, no, we'll have a lab in there, I think, before we start the next unit. Oh, it's 46 today. I'm going to go fill up my water bottle.
Miss,
Yes.
may I go talk to my counselor about my transcript?
For sure, yeah. It's due the weekend already. We're almost there. So close. One more block. Mm-hmm. Weeks like that. After the 3 4 weeks. Right? I know, it's terrifying. No. I mean, I look at it and I'm like, you know, when I say 4 weeks, I mean like go to about that 4th week and then like actually do that Friday.
Yeah.
Right? It's like, so I don't want to give you guys final and have to be marking it. Hi. That's probably. I'll probably be like. We like to find it a little fun. No love, no pressure. Colors are. Yeah. Or maybe not, is that I have to be not awkward. Right? So maybe I'll just be like, no, I'm sorry. And we could watch some cool videos. We could watch. I don't. Oh,
Today's Friday.
today's Friday. Yes. No, it doesn't go for another like 3 minutes. I don't know, 4 minutes. Yeah, it's 46 on Friday. And I kind of forgot, which is why I wrapped this up.
Yeah.
That's okay. Usually it takes me longer to teach to the block 8 and I don't know why, because like I just don't, not very much longer, maybe like 3 minutes. I like this unit because everything comes together, right? It's like, oh, I need to add this island. What do I need to add it with? Well, the whole, it is confusing, but what's going to happen is I'm going to pare it down for you, because right now, there's a lot of those calculations that we don't realize you don't right? And all this reasons about a buffer is so that you kind of understand it. And then all you need to know is that it can resist changes in pH, and that you might have a lot of each.
It's like, for this, like, especially considered, like,
Yeah.
there's like much less definition than the others.
Yeah,
Also the concept.
yeah, it's just like applications.
It's related to bio.
Which is kind of cool.
Yeah.
Yeah.
So I still remember.
So you don't like carbonate buffer, what?
I didn't like chill with that thing. It was the last unit and
Yeah.
I was very uni.
Oh, yeah, yes, you're a little busy.
Yeah.
Yeah.
I was I'm doing this against him.
Oh.
I'm trying to every day.
It's one of those days when I just want to like record and just play, but like recording.
Those are the like things.
Yeah, it's exactly the same lesson. It's a little bit different from time to time, like if you were to like listen to your lesson and watch the other one, there's like slight changes from time to time. Oh.
Yeah.
Yeah.
Just reading. Everyone's like around me like says that this is getting better.
It is.
Yes.
I think it's just because there are so many things going on, right? It's like, and they're similar. So it's really easy to kind of mix them up or get lost in it somewhere. It's kind of like, oh, it's like one of those puzzles that's 1,000 pieces and they all look the same, right?
Election code is also difficult, but I don't think we're gonna be able to end it, because we are no longer able to finish it, because we have, like, I used to be able to just finish it and have a review and final and whatever, but that was back when classes were longer, we had flex, I didn't have any hoops, I didn't have. For me, we still have. We will still discuss it, just won't be this big. Yeah.
Okay.
Yeah. Election.
Even when we don't finish it?
Oh, it won't be as hard. You'll get more of the easy stuff, the easier stuff is at the beginning.
Yeah.
Yeah. Okay, so it'll be easier.
We don't.
Yeah, exactly. Exactly.
Feel grateful though. Thank you. You're welcome. Have yourself a good weekend. Bye, Miss Spence. Bye. Hello.
Every day.
Sorry?
I was looking like.
Oh, it's sad.
I mean, you know, she was definitely sure on. She said you try to think that it parts of this together. Yeah, I'll just ask something. And when she got down. The girl, sorry. God, bro.
Better college student.
Okay, that's the investigation now.
What?
Yeah.
Fucking best friend. Rattled by fun, I'll probably come. Like, forget stuff, I'll probably come. Occasion, I'll probably come. I'm really, I like this house.
I'll be right there.
And then like, whatever. No, it's like. I probably. Obviously, right? We have to wear the obviously, right? Weeks. We're like best friends. It's like,
Wait, I thought. I still, I personally probably.
And everyone else thinks it's unforgettable. I think it's like the most realistic ever. And I hate it. And I still think it's funny. Because it's right, it's right, like my head. And I'm like, it's like, I run to anyone else, oh wow. One thing is like, no, it's like, and they never like talk to this guy yet. Like, oh, so you supposed to like something fast? Oh, you're just like, oh, I'm like, that's fine. Oh, no, like, I was like, you think, oh, I didn't know to Kenya. Kenya. Talk to you that way. It's like, you know, wow.
Yes. And you need the quiz.
Yeah.
Which quiz do you need?
Second one.
Yeah.
And then we do need.
And you have your periodic table and everything?
Yeah.
Perfect. Jody, did you have a question?
Yeah.
Yes.
I was just wondering, why is the final mole here the initial mole?
Because what we've done is we're doing a two-step process. This is our neutralization. And then these two set up an equilibrium. So we've produced these. Now, technically, all this really happens at the same time. But now these two set up an equilibrium in which we produce some H plus and some OH minus. They're not at equilibrium yet. We have this much of this and this much of this.
So basically, this one.
Yeah.
But while, as you said, this is technically.
Technically, it all happens at the same time, but you can imagine that it takes place like step A. This happens, blah, blah, blah. Now I have these, but they're not at equilibrium. Now they need to come to equilibrium. Yeah? So in our heads, because we're linear sequential people, not like everything happens everywhere all at once, right? Yeah. Yeah.
Fair enough.
Yeah. Good stuff.
Oh, and also, we use this table.
Yes.
We have mixing.
Yes. Yes. Okay, so ladies and gentlemen, we are having a quiz on Monday. Quiz on Monday on hydrolysis and mixtures of strong acids and strong bases. So this is section 5.3 and this is 5.4 A and B only. We're going to finish C today, but it's not going to be on the quiz. Okay, because it's mixtures of strong acids and weak bases. All right? So just 5.3, 5.4 A and B, it's on Monday. To that end, does anyone have any questions from some of the hydrolysis stuff that you were assigned last night? Are we all good with figuring out which is the predominant reaction?
Yep.
And if you're not, please feel free to drop by either after school today or the class.
kind of like, have you ever actually gone to Spanish? I don't think. Have you ever actually gone to Okay, yeah, this is the fact.
And your homework over the weekend is going to be to study for the quiz, okay? My other block talked me into it. I was like, page 74, and they're like, no, we're starting with the quiz. I'm like, okay. Anyway. Now, where were we? Oh, I need block 8. There we are. Nope, I need to go here. So when last we left off, we were on page 67. Okay, page 67.